If I want to do double integral 0 to 1, 1 to 2, x y squared dx. Dx, I guess, dy. Then if I look at this integral, then my inside integral is x y squared dx. When we take an integral with respect to x, we're going to treat it as a constant. Because we can treat it as a constant, we can take y outside of that inner integral. So we can rewrite it as integral 0 to 1 y squared integral 1 to 2x dx dy. So now, if you look at that integral, which now we have inside, this one, it has no y, it has no z, it has only x. And when you calculate in this integral, it's going to be a number. Because the definite integral, you can treat this as a number, so we can take it outside of integral with respect to y. Because that is a constant, we can push it outside. So what you're going to get is integral 0 to 1 y squared dy times integral 1 to 2 x dx. So we can separate variables with y on one side, with x on the other side, and multiply. So we're going to get y cubed over 3 from 0 to 1 times x squared over 2 from 1 to 2. So we're going to get 1/3 times 2 minus 1/2. So 1/3 times 3/2, so 1/2. In general, exactly the same thing will be happening. So now let me draw general setup. Here we have integral from a to b, c to d. And our function is a product of expression in terms of x and in terms of y. Then we're going to split that into product of one integral which will deal with x only, because we can just take your y's outside of integral with x, and we can take all x's outside of integral with y, and we can separate them and keep types in between. Example 0 to 1, 1 to 2, x plus 1 over y, dy dx. So if you look at that expression inside, that is x plus 1 times 1 over y. You see that it's product of two parts, one with x, one with y, so we can split them. So we can split them into integral 0 to 1 dx, integral 1 to 2 dy. And inside of integral with x, we're going to put all expressions with x. Inside of integral with y, we're going to put all the expressions with y. So we're going to get x plus 1 and 1. So we're going to get just 1 x squared over 2 plus x from 0 to 1 times ln of y from 1 to 2. So second integral equals to ln of 2. First integral equals to 1/2 plus 1 is 3/2. One more example. 1 to 3, 0 to 1, x plus 2y dy dx. So for this one, I cannot split x and y's. I cannot separate x and y's because I have plus. If it were times, it would be so much easier. So this one I will actually have to do the way it's written. Okay, more or less the way it's written. So we're going to get xy plus y squared, and y is from 0 to 1. An integral from outside 1 to 3 dx. So we're going to get 1 to 3 x plus 1 dx. So we're going to get x squared over 2 plus x, 1 to 3. So 9 halves plus 3 minus 1 half minus 1. So 4. It is something like that. One more example. Now that's example. It's going to kind of lead us to our double integral, but we start with iterated. So we have integral 0 to 1, 0 to 1, and x e to x y dx dy. If I try to proceed with this integral, then I will need to find antiderivative of that middle one. So I'll have to do integration by parts. And I'm going to write it here. It's doable. Actually, it's not too bad. But there is a better way. So that's what we'll try to do. Okay. So that is, again, doable, and it probably will take us 5 minutes. If we recall what integral by parts is, it will not be too bad. But actually, there is an easier way. So let's do an easier way. That's kind of possibility. But now let's do it over there. So the over way will be, rewrite that as your double integral. Okay. And double integral tells us that double integrals to e equals to iterated integral, where we'll have dx dy, or it equals to iterated integral where we have dy dx. So we will have one with dx dy, so we'll try to switch and we'll write down dy dx. So we'll keep our function. And what we did, we flipped the limit of integration. Instead of going dx dy, we're going dy dx. Why that helps? Because if you look here, if you like do substitution u equals x times y, and antiderivative x times e to xy with respect to y is going to be e to xy. And we do it from y equals to 0 to y equals to 1. And outside, we have integral 0 to 1 dx. Substituting 1, substituting 0 for y into that expression, we're going to get, if substituting 1, we're going to get e to x. If substituting 0, we're going to get 1. So we're going to get e to x minus 1. So we're going to get e to x minus x from 0 to 1. And we're going to get our final answer. Substituting 1, we're going to get e minus 1. substituting 0, we're going to get minus 1. So we're going to get e minus 2. Okay. So that is a little bit easier to calculate. So sometimes when we working with the iterated integrals, we'll flip the limit of integration. We'll, instead of going dx dy, we'll go with dy dx. Especially, that's easy to do if we will have rectangular regions. And let me do an application of double integral. So remember what double integral is. So we have our region R. Okay. Rectangular region R. That's kind of our domain. And that domain is somewhere on xy plane. Right? So it's somewhere on xy plane. Okay, xy plane. Then we also have like our z-axis somewhere here. And what we did is we divided our region into smaller rectangles, right? In particular, we look at one rectangle, this one, rectangle number I and j, and we take the area of that rectangle, area of that small rectangle. So we take area of Rij, so I'm going to call it delta A. So that's area of that shaded small rectangle. And we multiply it by value of function somewhere on a point, somewhere in that rectangle. So we pick a point, okay? And then we multiply that area by value of function at this point, x, I, y, j. Okay. So that's the red point. It's our red point, okay? So we evaluate the function. And often when we look at the function, we treat z as a function of x and y. If we treat z as a function of x and y, then f of xy will be somewhere here. Somewhere here, right? So that is height. So that's going to be f of x, I, y, j. Okay. And if I multiply the height by corresponding area, then I'm going to get this kind of rectangle, if you can see that rectangular box. Area of that rectangular box, if you can see it. So that expression equals to volume of that box. Volume of that box. Okay, this box. Okay, so each of these is going to be volume of that box. So the idea will be eventually what we're going to get is when we're going to add up all those boxes, we're going to get approximation for volume under the curve, for volume under the surface. Okay? So if in calculus 1 we got approximation to the area under the curve, and area under the curve were approximated by the rectangles, here we're going to get approximation to the volume of under the surface, and we approximated it by volumes of rectangular boxes. Okay, so that's an idea. So I guess I'll move on to the next page and I will write down what to get. So limit as delta x approaching 0, delta y is approaching 0, sum I from 1 to n, sum j from 1 to n, f of xi, yj multiplied by delta a equals to double integral over region R, f of x, y, dA, and it equals to a volume under the surface z equals to f of x, y over the region R, which is in our case rectangle AB plus CT. So if in calculus 1, our singular integral represents the area, here double integral represents the volume, assuming the function is positive. Assuming f of x, y is positive. Assuming the function is, the surface is above x, y. So the same assumption as we did in calculus 1, assuming the function is positive. Then in calculus 1, the integral will calculate area. Assuming function is positive, in multivariable calculus, function calculates, double integral function calculates volume.